This is the second worksheet, and we have significant figures, concept, dimensional analysis, and isotope and atomic mass. The first thing you need to do is writing your name and student ID. I keep telling you this until the last worksheet because I know I might still get some worksheet without name and student ID, and that would be 0. Okay, so let's go to the worksheet. The first one, we are working with the significant figure concept. So we had, I think, enough practice in the lecture slides, so let's do this. These numbers and find how many significant figures each one have. So the first one have 1, 2, 3, 4, 5 sigfigs. This one we have leading zeros. We do not count leading zeros as significant figures, so we have 1, 2, and 3, so 3 sigfigs. This one, the leading zero is not counted. The trailing zero with decimal place, we count them, so 1, 2, 3, 4 sigfigs. This one, we have the decimal place, and we have trailing zeros, and we count them, so we have 5 sigfigs. This one, there is a trailing zero without a decimal point, so we don't count it, so it's 1, 2, 3 sigfigs. Well, I don't know why I put that dot there. So 3 sigfigs. Okay. So question number 2, tracking the sigfigs in the multi-step processes. So I also write this here. I explained this in the lecture slides. The rule of PEMDAS that says that parentheses goes first, and then exponents, and then multiplication, division, and addition, subtraction. Okay. So if you have a ratio like this, if you don't see the parentheses, you have to apply the parentheses, which means that you have to do whatever inside the parentheses first. Okay, so we have addition over there, so it's 136, and you align them where the decimal place is, 0 to 8, and 0 here, it's a plus, so it's 8, 8, 3, decimal place, and 1. Okay, so I write these here. So on top we have 1.388. How many significant figures do we have? So we have to cut it from here. I do this in blue. So this is the last significant figure. So I underline the last significant figure. So I know that I have 3 sigfigs, but I write 4 digits. Okay, and on bottom we have 6219. So when you divide these two, you will get 2.2318. Always write 4 decimal places when you use your calculator for division or multiplication, and then go back and count 4 significant figures to track how many sigfigs we need to report in. So here, this one, how many sigfigs do we have? We have 4. On top we have 3. We write 4, but it's 3, that's why we underline this. We have 3 sigfigs, so the rule of division says the smallest number of sigfigs. So 1, 2, 3, we have to cut it from here, therefore it's 2.23. Okay, next one, again, first you apply parentheses, and you have to do whatever inside the parentheses. On the top we have the number, it's okay. The bottom is a subtraction, so it's 4.198, decimal place, 6 and 0. It's subtraction, so it's 8, 9, this is 3 and 11, so it's 5, decimal place, and 3. Okay, so we have to let's make it with blue. So we have to cut it from here. Okay, so if I want to round this, I keep saying that. Do not round it. Keep whatever you get and underline the last suffix. If you want to round this, it should be 3.6, right? This is 9. But we do not round it. We just keep the whole number. So on top, we have 39.6. On bottom, we have 3.598 and underline the last suffix. So if you do that division in your calculator, you will get 11.0061, always 4 decimal places, and then go back and count 4 suffix. So on top, how many suffix do we have? We have 3. On bottom, we have 2. We only count these 2. So 2 suffix here, 3 suffix on top. So the final answer should have 2 suffix, 1, 2. So we got it from here. Therefore, the final answer is 11. Okay. Next one. So the PEMDAS says whatever inside parentheses, so we have to do inside the parentheses. So 27 plus where decimal places here, 8, 0, addition. So in addition, we know that we should put the smallest number of decimal place, right? So how many decimal place the answer should have? Right, it should have 0 because this 27 doesn't have anything in front of the decimal place. This one has 1, so the final answer should have 0. Therefore, the last significant figure is 7. Okay, so I rewrite this here, so 27.8, and underline the last suffix, multiply. Okay, so if you multiply these two numbers, you will get 0.2556. You probably have more digits in the calculator, but you only write 4 decimal places. Okay, so now let's go back and see how many suffix we need to report. So multiplication, you have to see how this, you have to go with the smallest number of suffix. So this one here have 3 suffix. This one here have 4 suffix. So how many suffix the answer should have? 3. This one is 3, this one is 4. So starting from here, 1, 2, 3. So this is the last significant figure. Okay, and you multiply these two. There's a multiplication, and the answer is 7.1057. Again, 4 decimal places. And then you have to count how many suffix you need to report in. So how many suffix do we have in this one? We have 2. We write 3, but we have 2. And in this one we have 3. So the answer should have 2. 1, 2. We cut it from here. Therefore the answer is 7.1. Okay. Next question is dimensional analysis. So with the for a dimensional analysis, we have to set up the chart as I told you in the lecture notes. We make the chart of given, wanted, convert, and no. What do we know about this conversion? Okay, what is given? Reading the question, you see the data that is given is the density. So we have the density as 7.87 gram per cubic centimeter. What is wanted? It says what is the density in milligram per cubic inches. So we want the density in milligram per cubic inches. Okay, what do we want to convert? Well, if you look at the units, you see that we have to convert gram to milligram, and we have to convert cubic centimeter to cubic inches. What do we know about these conversions? So we know that 1 milligram is 10 to negative 3 gram. Okay. Do we have any conversion that directly relate cubic centimeter to cubic inches? No, but we know that 1 inch is 2.54 inches, centimeter. But we need this cubed, so we can cube the whole thing, and when you cube it, the cube goes to every single one of these. So it's 1 cube, inch cube, 2.54 cube, and centimeter cube. Okay, so 1 cube is still 1, so we don't need to write cube, so I erase this. Okay, so 1 cubic inch is 2.54 cube of cubic centimeter. Okay, so it seems like now we have all the conversion that we need. So always we start with the given information. So 7.87 gram, and I told you before, so whenever you have a unit which is in a ratio, you can write it like this. So in 1 cubic centimeter. So the density is gram per cubic centimeter, so it means that 7.87 gram is 1 cubic centimeter. Okay, so we have to apply our first conversion. We want to go from gram to milligram. Okay, the gram is on top, so I want to get rid of that. I have to put it on the bottom. So if I look at my conversion factor, well, look at my equality here, I can get a conversion factor. So 10 to negative 3 gram is 1 milligram. Okay, so I can cancel gram with gram. I have milligram here. That's good. So the next conversion is going from cubic centimeter to cubic inch. So I have cubic centimeter on the bottom. I want to get rid of that, so I have to put that on top so it can be cancelled with that. And from my equality here, I can say that 2.54 cubed is 1 inch cubed. So I can cancel this with this one, so I have cubic inch. So the units left is milligram per cubic inch, and that's what we want. So as soon as we are good with the unit, we are done. Okay, so it's milligram per cubic inch. The rest is just putting these numbers in the calculator, and if you do so, you will get 1.2897 times 10 to 5. And if you track the sig figs, so these are exact numbers, we do not count for these. So the first number that we started with had 3 sig figs, so the final answer also should have 3 sig figs. So it's 1, 2, 3, we cut it from here. The next number is 9, so we have to round up. So the answer is 1.29 times 10 to 5 milligram per cubic inches. Okay, so moving to the next question. Again, we have to make the chart. Given, wanted, convert, and what do we know? Okay, so what is given? A patient is prescribed that amount of drug, so we have 0.300 milligram of the drug. Okay, is available in 50 microgram tablets, so that's also a given information. So we know that one tablet equal 50 microgram. Okay, it says they're available in 50 microgram tablets. So one tablet is 50 microgram of the drug. How many tablets are needed? So what is wanted? What do we want? So we want the number of tablets. What do we need to convert? Well, we have milligram to microgram here. So we have to convert milligram to microgram, or maybe microgram to milligram, no difference. And we have to end up with a number of tablets. Okay, so what do we know about this conversion? So if you look at the chart of prefixes, there is no equality that can relate milligram to microgram, but we know that 1 milligram is 10 to negative 3 gram, and 1 microgram is 10 to negative 6 gram. Okay, so these two are grams, so we can relate those, so we can relate milligram to microgram. Okay, so let's start here. Let me change the color so it doesn't mix up with the top. So always start with the given information. We start with 0.300 milligram of the drug. Okay, so we want to convert that. So we have to go from milligram to gram because our equality here is milligram to gram. So milligram is on the top. I want to get rid of that, so I have to put it here so I can cancel it. And looking at my equality, it says 1 milligram is 10 to negative 3 gram. Always first find which unit goes where, and then look at your equality. The top and the bottom of your ratio of your conversion factor should be equal. Okay, so you can have the ratio equal to 1. Okay, so I can get rid of milligram with milligram, and now I have gram. Let's continue. So with gram, I can go with microgram here. So gram is on top. I want to get rid of that, so I have to put gram here so I can cancel it. And looking at my equality here, 10 to negative 6 gram is 1 microgram. Okay, so I can cancel gram with gram, and I have microgram here. Are we done here? Well, not quite. What is wanted is number of tablets. So we need one more conversion factor to go into number of tablets. If you see in the given information here, we have one equality, and from any equality we can get a conversion factor. So we want to go from microgram to number of tablets, and that's what equality is giving us. So I want to get rid of microgram, so I put microgram here, and from this equality I know that 50 microgram is 1 tablet. Okay, so I can get rid of microgram with microgram, and I end up with number of tablets, and that's exactly what we need. Okay, so we are done here. So the rest is just putting these numbers in the calculator, and what you get is, let me write it with blue, what you get is 6.00 times, well, there's no times, it's just 6 tablets. So it's 6 tablets. We started with 3, we end up with 3 suffix. Okay. Okay, the last two examples, two questions are for average mass. So we have two isotopes for copper. One isotope has the mass of this. Remember, for the atomic mass, we show it with AMU, atomic mass unit, or U. It's the same thing. And so we have one isotope with this mass and this natural abundance. It's asking for the natural abundance and isotopic mass of the other isotope. So you remember the atomic mass unit, formula was M equal, let's write it with red again. So M equal M1 x1 plus M2 x2. So we have M1, we have the mass of our isotope, we have the natural abundance of the first isotope, but it seems like we don't have anything else, and it's hard to find all of these. But if you think about it, you can always find the atomic mass of any element from the periodic table. So you can look it up, and for copper, the average mass, the atomic mass is 63.546. Okay, so we have this, but still we have two unknowns, and we cannot solve one equation with two unknowns. So if you only have two isotopes, the sum of x1 plus x2, the sum of natural abundance is always equal 1. Okay, that's another formula we can use. So we know x1, we can find x2. So x2 is 1 minus x1, and it's 1 minus x1 was, well, it's in percent form, so we have to make it in ratio form. So it's 0.6915. So x2 is, let me check, so it's 0.3085. Okay, so now that we have x2, so we are solving it for m1. Okay, so you just need to put all of these numbers. I don't want to write all of them. You need to show your work and show how you solve this. But if you plug all of these numbers inside this formula, you will get M2. Let me write it with a different color. You will get M2 as 64.93 U. Okay, you have to show your work, plug these numbers, and find the M2. Okay, for the last question, so this same type of question, we have two isotope, we have the mass of two isotope, and it's asking for the natural abundance of both of these. So again, the same formula, M1 x1 plus M2 x2. Okay, so we can find M from the periodic table, and the M for gallium is 69.723. We have M1, we have M1, we have M2, we have M. We need to solve it for x1 and x2. Again, we cannot solve one equation with two unknowns. But if you think about it, we know this is 1, right? So x1 is 1 minus x2. Okay, so if you plug this inside that equation, let's say, so if you plug x1 into here, you will have M equal M1 times 1 minus x2. I just put what is here instead of x1, okay, plus M2 times x2. Okay, so now I have M, I have M1, I don't have x2, I have M2. So you only have one unknown, both of them are x2, and you can plug these numbers in and find the answer. Again, I'm not going to go through this, but you have to show your work. I give you the final answer. So x1, x2 from this uh, formula, you will get 0.6011 for x2, and then you put this x2 into this formula and solve it for x1, and then x1 will be 0.3989. Okay, so these two are the final answer for the last question. Okay, so again, you have to show your work. I just give you the final answer and showed you how you can get these answers.